determining the solubility of an insoluble salt if you're given the KSP. Okay, so if you're given the KSP of MX2, again, this is a fictitious compound, so you can just say that that breaks up into M and 2X, okay, with some charges there. Okay. So what would be our KSP for this, the expression for KSP? KSP would be the concentration of M times the concentration of X squared, right? So let's set this up. You have initial conditions would be, you have an excess amount of solid because you're making a saturated solution. So anytime you're dealing with a solubility problem, you have, in order for you to get an ion product, a Q that's equal to KSP, you have to have some excess, at least some excess solid there. The activity would be 1. Okay. The changes would be what? You have minus X. So X would be the solubility in moles per liter. And you're going to make X moles per liter of M and 2X moles per liter of X. So at equilibrium, you still have an excess here, okay? At least you have to have at least some solid. You have to have a saturated solution, and then you have X moles per liter of M and 2X moles per liter of X. Okay, so what's our expression for KSP in terms of X? This is going to be X times 2X squared. And we're given the KSP is 1 times 10 to the negative 10, so we say that that's equal to 1.0 times 10 to the negative 10. What would be our X? Therefore, here, you'd say X times 2X squared is how much? What is that? 4X cubed, right? So that's equal to 1.0 times 10 to the negative 10. So how do you solve for X? X cubed is 1.0 times 10 to the negative 10 over 4. So X would be equal to the cube root of that number. So what is that number? 1 times 10 to the negative 10 divided by 4 equals that. And take the cube root of that, so that's 2.9. Oops. Okay, this is 2.5 times 10 to the negative 11, and the cube root of that, oops, is 2.9 times 10 to the negative 4. So the solubility is 2.9 times 10 to the negative 4 moles per liter. So if you know the KSP, you can predict how far your solid will dissolve. Now, one thing you need to worry about here, if you're given a real compound, okay, if your anion, let's say your anion is carbonate, okay, the solubility that you calculate would actually be less than what you would expect, what you would get experimentally. And the reason for that is why? Your carbonate can actually hydrolyze, right? And it will give you HCO3 minus plus OH minus. So there's actually a reaction that's taking carbonate away, so it's going to shift your equilibrium further to the right. So the actual solubility in reality is going to be a little higher. If your ions can hydrolyze, you have reactions that are removing those ions. So if you're removing these ions right here, okay, if you have some other stuff in your water that are removing this, then the Chatelier's principle says that shifts that equilibrium further to the right. Okay. Now, for simplicity, unless you are told to consider the hydrolysis and you're given the actual values for the equilibrium constants for the hydrolysis, just assume the simplest case, which is ignore the hydrolysis. Okay. And calculation gets a little bit more involved when you have to take into account the hydrolysis.